Hello everyone. In this video, I will cover the third problem of the 2020 December contest. So this problem is definitely the hardest of the three. So let's go ahead and cover what the problem is asking. Essentially, you have a bunch of cows on this very large grid, and they either move north or east. And so at each moment of time, each of the cows are going to take one step forward in their respective directions. And they're going to keep moving until they reach some cell that has already been covered by another cow. And so I'm going to go ahead and actually show off this little Desmos screenshot I have right here. So this represents the sample case. And in this case, what happens is you have these bunch of cows. These little dots are like where they start. So you can see like this is where they start, right? And so, for example, let's look at this cow. This green cow, all right, let's look at this cow first. This cow. So this cow is going to keep going and it's going to keep going until it reaches this cell. And now this cell here, actually at this point in time, the other cow, the purple cow, would have reached about here because they all move at the same speed. And so at this point in time, the purple cow hasn't reached its spot yet. So this blue cow right here is the first cow to reach this spot. So the blue cow is going to just come through here just perfectly fine. So it's going to come through here. It's going to just keep going here up to there. Now by the time this purple cow gets here, in I believe 1, 2, 3, 4, 5 steps, whereas this in 5 steps would have already reached over there, you can see the purple cow reaches a spot where the blue cow is already covered. So in essence, this purple cow gets blocked. And so this purple cow can't move anymore. And so it stops. On the other hand, as you can see here, this blue cow will be blocked by this other blue cow, because this other blue cow would have already reached here by now. Remember, they all move at the same speed at the same time. So this other blue cow gets stopped. And then this blue cow would have gotten stopped here because this other green cow would have already reached that spot a long time ago. And then finally, this green cow never stops. It just goes on to infinity. And so the problem is basically asking us, when does each cow stop, if at all? That's basically what it's asking, right? And so there are a number of ways of doing this. So the first idea you might have when looking at this problem is maybe some sort of simulation. So we just keep incrementing the time one by one. At each time, we bump each of the cows forward by one step, and then we see after how many steps does each cow stop, if at all. And then in order to deal with infinity, we might just bump it like some large number of times, like maybe like, I don't know, 1,000 times or something like that. And then after 1,000 times, if a cow still hasn't stopped, we're going to assume they go on to infinity. This would work if the coordinates were small. But unfortunately, if you want to get the full points for this problem, full credit for this problem requires the coordinates being up to 10 to the 9, and 10 to the 9 is way too much to simulate. And so the modified idea is we're going to still simulate, but simulate faster. You've probably noticed by now that not all the time periods or not all the moments of time matter. So here's a simple example. Let's say we only have 2 cows. Let's say the distance here is going to be 8, and the distance here is going to be 6. Well, time 1, 2, or 3 don't particularly matter, because in each of these times, the 2 cows still have not collided yet. We only really care about time 6 and time 8, right? And so what we should be doing is some sort of simulation where we only check the times in which some cow reaches an intersection point. Those are the only moments in which a cow could potentially stop. And so that severely reduces the number of time points we have to check from like maybe like 10 to the 9 to just just between each pair, or O of n squared different time points. Now this is still pretty annoying to implement, so but I guess there's a nice way to implement this that I will show off in a second. So a nice way to implement this is to sort all the intersection points. So let's say I process, let's just take a few examples. I'm gonna go ahead and just take a few examples like this point, this point, this point, this point, all right? So this point is at coordinate 5 and that should be 5, yes, right? And it's at 5, so I'll put it here. This first point right here, I'll mark these 1, 2, 3, 4. So this first intersection point, for example, is at x equal to 5, y equal to 5, time is equal to, like, the time is basically time for the first cow to get there is going to be 2. Time for the second cow to get there is also going to be 2. And by the way, if this problem specifies that if the two cows reach the same point at the same time, then neither of them get blocked. They both keep going. The second point is going to be, I think it's x equal to 5, y is equal to, what is y equal to? Y is equal to 6, right? Yes, 6. The first cow, and when I say first cow, I mean the cow that reaches there earlier. So the first cow reaches there just in 1 time. The second cow takes 3 times to get there. The third cow, or the third intersection spot, is at x equal to 11. Y is equal to 4. The first cow takes time 1 to get there. The second cow takes time 2 to get there. And I think you get the idea. And what I'm going to do is I'm going to process all these intersection points in increasing order of time 2. Now, you might want to take a moment to pause the video now and think, why time 2? Why not sort by time 1 or time 1 plus time 2 or some other metric? Why are we processing the intersection points in order of time 2? And I recommend you pause the video and think about why that's true. But yeah, we process them by time 2, mainly because we want to check when cows get stopped. And so in this case, it's already conveniently in sorted order. So what would happen is I would process this one first, then this one, then this one. And at each point, at each intersection point, I just want to check, does the later of the two cows get blocked by the earlier of the two cows? And the earlier cow only blocks the later if the earlier one was not stopped earlier than time 1. So that's a little confusing, I know, but like, essentially, let's do a little example here. This cow's going up, this cow's going this way, and let's do this cow over here is going this way, right? So in this case, this left cow kind of gets, this guy kind of gets stopped very early on because it gets blocked by this person or this cow. So then this other cow right here, when we process this intersection point, this cow doesn't actually get stopped because the time at which the other cow stopped is earlier than the time it takes to reach this intersection point in the first place. And so it doesn't stop the other cow. And so this green cow just keeps going. Yeah, so let's go ahead and implement that idea now. And I'm going to go ahead and show some, yeah. So if you're still a little confused, I think the code will help clear things up. So let's write some code. So we need, let's see, our IO stream, our vector, and we need algorithm because I'm going to be sorting. Awesome. So what information do we need? We need n, the number of cows, and then we need x and y. And we need direction. Okay. So let's see. So this will be the direction. I'm gonna read in all three of these values for each cow. I'll just do that. And now what's next? So now we want to go ahead and generate all the intersection points. Now for here, I'm going to do something a little fancy. I briefly covered this in the last class, but you might not remember, but we covered something called structs, which are basically like custom data types. Now, if you don't remember how these work, you could have also used like a vector during the context of some other like thing. Just basically anything I can store like up to like anything I can store like an array of 4 numbers or something. But anyways, here I'm going to go ahead and store for the intersection points, which is characterized by it's characterized by what I want to save. I want to save the 2 cows that are involved in this collision. I'll give them better names, cow 1 and cow 2. So these are the 2 cows involved in the collision. The time it takes for the first cow to hit the point and the time it takes for the second cow to hit. And I'm also going to define a comparator. So this is a little fancy. So basically what I can do is I can define a comparator for how a struct is sorted. Now you don't need this to solve the problem because n is so small, n is just 50, that instead of directly sorting each of these points, instead of directly sorting them, I can just naively iterate each time. So I can iterate over and find the smallest intersection point, remove it, iterate over, find the second intersection point, remove it, iterate, find the third earliest intersection point, remove it, and so on and so forth. I can just do it that naively, and that'll take like I think n to the 4th. However, I'm sorting here just because well, I guess it's a new concept, so you can check it out. So essentially, sorting just lets me. This is a bit of a magic here if you don't know it, but you can look it up if you're interested. Again, it's not necessary, but it makes the problem easier, in my opinion, to implement. So this comparator is just going to define what it means for one intersection point to be less than the other. So it gives the program some sort of order for sorting these intersection points, because otherwise it has no idea how to sort intersection points. So we want to sort them based on time. And if the, let's say if the times are the same, then we can just sort by some, it doesn't really matter what we sort by then, because all these collision points happen simultaneously. So I'll just go ahead and sort it by, I guess, cow 1. Sure. 2, oh. If these are also the same, we can sort by cow 2. And if those are also the same, I'm going to sort by time 1. Yeah. This is just completely arbitrary. So it's completely arbitrary since intersection points at same time are simultaneously there we go, processed anyways. Yep. So this is just necessary to not make it like crash, and it's a bit complicated to explain now. But anyways, it's the main idea is that we're sorting by time. That's the main idea. The main idea is sort by time 2. So let's go ahead and now let's go ahead and iterate over each of the first cows, each of the second. So iterating over all pairs of cows. And now the interesting thing about, or I guess the nice thing about this problem is that they guarantee all the x and all the y's are distinct. So if two cows are facing the same direction, they will never intersect. They'll be like parallel lines. So we only need to consider if the two directions are different. So in that case, one of them is facing east, one is facing north. And so I'm actually going to do a little implementation trick here, because normally you would have to consider two different scenarios. Is cow I facing east and is cow J facing north, or is cow I facing north and cow J facing east? So I'm going to go ahead and process both of them by doing the following. I'm going to declare new variables. I'm going to say if the direction of A is equal to north, I swap the two of them. And so what this does is now it guarantees that whichever cow is A is the one that faces east and B is the one that faces north. So this just lets me process both cases with one piece of code. So it's a bit more efficient that way. So now what do we want to check? Let's see. So time A, bad choice of names. Time A is going to be the time it takes for the cow A to reach the intersection point. That is it will be x of B minus x of A. Actually, first we need to check that's even the right orientation. So like, for example, like if it's like something like this, right, then these two cows will never intersect. So it has to be a scenario where it's like that. So we need to first ensure that XA is smaller than XB and YA is bigger than YB. And you can always pause the video and scrutinize over why exactly these are the case. It's just a bit of math and like looking at the orientation. Time A is that, time A is that, and time B is equal to this. Again, you can just look at the diagram and see why that's the case. So now, if time A is larger than time B, that means time A gets there later than time B. I'm going to create intersection point. Intersect. Yeah. So I'm going to go ahead and now just, if time A is greater than time B, then let's see. I want to then process cow. Then that means, what does that mean? That means cow A is the one that is potentially blocked by this scenario. So in this case, that means cow A is the one that reaches later. So it's time. So that means time 2 would be time A's time. Time 1 would be time B's time, and therefore the order is like so. Otherwise, it's the other way around. Actually, otherwise, if time A is smaller than time B, it's the other way around. And then you can see here there is no else, because if time A is the same as time B, then both cows keep going. So we can just ignore that intersection point. Okay, so now we can sort the intersection points. And now let's go to the third step of this algorithm. The third step is going to be now processing all the intersection points in increasing order of time. So here I'm going to create a new variable called stopped. And stopped is going to be of size. is going to be the time at which the cows stop, or infinity if they never stop. In this case, coordinates are up to 10 to the 9, so I believe a large enough, let's just do 2 times 10 to the 9, for example. That will always be large enough. So let's say infinity is going to be 2 times 10 to the 9. So we'll do that. And so now, let's go ahead and process each of the intersection points. Okay, let's process each of them. And here's what I'm going to do. For each intersection point, we want, let's see, we want to make sure that first off both cows haven't stopped, basically. So let's see. So cow 1, I realize I'm mixing 1s and 2s and A's and B's. I apologize for that, but that just ended up happening. So if time 1, so that's the earlier of the 2 cows, actually made it to this intersection point. So they actually didn't stop at that intersection point. Right? I guess this is the stop time. And same thing, if cow 2 actually makes it to the intersection point, then cow 2 gets stopped. Stopped because it was the slower of the 2. So cow 2 gets stopped, and its time is equal to that. Great. At the very end, let's print the answer. So if the stop time is infinity, that means it never stopped, then it's just infinity. Awesome. Let's test that now. 5, 3, infinity, infinity, 2, 5. That's correct. So, all right. And it works. Awesome. Yeah. So once again, I want to just reiterate that you didn't need to use structs to solve this problem, and you didn't need to do any of this stuff. This is like more advanced stuff that makes the problem easier, in my opinion. But instead of sorting here, you could have just as easily just like not sort and instead just iterate each time to find the minimum time intersection point, and that will give you O of n to the 4th, which will also solve the problem. So you didn't have to use some sort of sorting to solve this problem. But yeah, so it's also possible to not sort. But yeah, that is the general gist of how to solve problem 3. It's just it's simulation but done efficiently. It was a bit of a doozy to implement, but so hopefully if you didn't solve that problem, you learned something, and even if you did solve that problem, maybe you learned an easier way to implement the problem. Or maybe not easier, but this is like, I think, probably shorter code than most. Okay, so thank you for watching.